Welcome back. In this video, we're going to talk about game theory. And in particular, we're going to talk about strictly determined games. So game theory is probably not what you would think it would be based on the phrase game theory. It's not necessarily about games. It can be applied to games, but game theory is really a topic in economics. So it's about risk and reward and how two players who have opposite goals make decisions based on trying to win the game or win the situation, whatever it is. So this is applied in economics, it's applied in business, it's applied in military defense strategy. It has applications in a lot of different fields. So just because it says game in the title doesn't mean it's necessarily just about children's games, although it can be applied to those things as well. So in this section, we're going to talk about just two-player games. So we have two players. Those players could be teams, or they could be individuals, or they could be companies. But there's only two. And then we're only going to look at what are called zero-sum games. And so a zero-sum game is when there is a finite amount of money or resources that can be gained from the game. And if one player loses, the other player wins that exact same amount. So no money's coming in, no money's going out. Money is only exchanged between the two players. And it's not necessarily money, though I'll use money as an example for most of the examples just because it's kind of easy to understand. So, all right, so I'm going to use an example, a very easy example to kind of understand how game theory works. I used to use a slightly different example, and then I had a student who's a mother of two children come up to me after class one day and say, "This is what I do with my kids." I didn't realize that was game theory, and it's actually a really, really good example. What she said was that when she wants her children to share something like a snack, so let's say it's a bunch of goldfish crackers, and I'm going to draw a bunch. I am not an artist, so all right. So there's 10 goldfish crackers. And so let's say one child has the goldfish crackers and the mom wants them to share them. So they say, share some crackers with your sibling. Now, if the child with these 10 goldfish crackers is told to share, but is not told to share how much, then maybe they'll, take two off. These are the ones that they're going to share. And then they'll keep most of them for themselves because children, and really humans in general, are selfish. Not always, but frequently we are selfish beings. So what she decided to do to try to make it as fair as possible was she decided that when she wanted her kids to share a snack, she would tell them, okay, one child, child A, you're going to make two piles of snacks. You can divide it however you want. You're in charge of making the two piles of snacks. And then child B, the other child, gets to choose which pile of snacks they want. So what happens is probably exactly what you would expect to happen. If a child was told, okay, you get to split these 10 goldfish crackers up into two piles, but your brother or sister, they get to choose what pile they want, they're going to count them out. And that's what she said happened. She said they were very meticulous. They would make sure they counted out exactly half of the crackers or M&Ms or whatever it happened to be that they were sharing. And they did that because they knew if they divided exactly in half, then their sibling couldn't take a bigger share. They were guaranteed to get half. And so really what they were doing was they were minimizing their losses. They could have made one pile bigger than the other and hoped their sibling didn't count or was generous, but they could guarantee they get exactly half if they make the piles exactly half and half. And so that's really what game theory is about. We're not shooting for gaining the most. We're really trying to minimize our losses. And so this property or this theorem is called the minimax theorem. We're trying to maximize our gains really by minimizing our losses. And so that theorem, we're not really going to talk about that in this class, but that's just kind of the basis of game theory. So in everything we do, we're going to try to play it safe. So we're going to assume that the other team does not have our best interest at heart. And so we're going to try to do as best as we can, knowing their goals are completely opposite of ours. All right. So let's talk about a few things. We'll start with a saddle point. So a saddle point is an element that is the smallest entry in its row and the largest entry in its column. And so saddle points only occur when it's a strictly determined game. So that's a good thing to know. So let's look at an example. So this is a very unrealistic example, but pretty easy to understand. So let's say we have two teams, Team A and Team B, and this is a made-up football game. So Team A is on offense, and Team B is on defense. Each team has 3 different plays. So that's what the numbers outside of the matrix represent, the 3 different plays. Team B has 3 defensive plays. Team A has 3 offensive plays. And then the numbers inside the matrix represent the yards gained or lost by Team A. So I want to write this down. The numbers are always in terms of player A. So positive numbers are good for the offense, right? They want to throw the ball or run the ball as far down the field as they can. So this 12, for example, that's a really good value. They gain 12 yards. 9, also a pretty good value. -5, that's not good. That means they lost 5 yards. This also means that all of the values are completely flipped for Team B. Because for Team B, that +12, that's bad. That means the offense gained 12 yards. They did not do a good job at stopping the offense. Whereas -5, that's a really good value. They pushed the offense back 5 yards. So anytime we're looking at a matrix, it's really, really important to know whose perspective we're looking at it from. So sometimes we're going to look to see better options for player A. Sometimes we're going to look to find better options for player B. But the numbers, they're always in terms of player A. So positive is always going to be good for A and bad for B. Negative is always going to be bad for A and good for B. All right, so let's look at this matrix. So let's start off by looking at from Team B's perspective. So Team B has these 3 plays. And they know all of these numbers. Team A knows all of these numbers, which is, again, why it makes it a very unrealistic example for football. So if Team B chooses option 1, then the outcomes are either Team A gains 9 yards, Team A gains 12 yards, or Team A loses 5 yards. Okay, so that column actually contains both the worst option for Team B, the +12, and the best option for Team B, the -5. So that's kind of a risky option. If Team B chooses option 1, it could be really good or it could be really bad. If they choose option 3, either they make the offense lose 4 yards, that's good. The offense gains 6 yards, that's not great. Or the offense gains 3 yards. It's not terrible, but it's still not great. So again, option 3, some good, some bad. So if Team B chooses option 3, they're not sure what's going to happen. Option 2, however, the outcomes are either Team A loses 3 yards, Team A loses 1 yard, or Team A loses 2 yards. That's a great option because Team B knows they can make them lose yards no matter what play Team A picks. That's a great option. So Team B, they're always going to pick play number 2 because there's no guessing at what's going to happen. Now again, the biggest negative values aren't in that column. But that's not what we're concerned with. We're concerned with playing it safe. And playing it safe is we know if Team B chooses option 2, Team A is going to lose. All right, so Team A also knows this. So Team A, looking at their options, Team A essentially is only concerned with that middle column now because they know what Team B is going to do. So what's their best option based on the options they have? Well, if Team B is going to choose this middle column, then Team A's options are either lose 3 yards, lose 1 yard, or lose 2 yards. And if they have to choose between those 3 options, well, losing 1 yard is definitely the best option. So they're also going to pick option number 2 every single time. So this is what we call a strictly determined game. So in this example, there is no way either team would ever choose a different option. That is the best option. Now, for Team A, that's not a good option. That's still them losing 1 yard every single time. But that's the best they can hope for given this scenario. And so the saddle point is not necessarily a good option for either team. In fact, it's actually not a good option for either team, but it's kind of a balancing point where it's their best option given the circumstances. And that's why it says, so a saddle point is an element that's the smallest entry in its row. So that small values, so row, that's player A. So A is the row player. Smallest entry in a row, that's the worst value in the row for Team A because they want larger values. They don't like smaller values. Largest entry in its column, so column player is Team B. Large values are bad for Team B. So that means that's the worst value in that column for Team B. So it's kind of this balancing point of it being kind of a mixture between a bad value and a good value. It's just kind of a balancing point. So anyway, the way I would recommend solving for a saddle point, this made-up example, it's not going to be that easy in most examples. I made the second column all negative so that it would be pretty obvious. It's more than likely not going to be that obvious in any of the examples you do. So here's how I would do it. So the saddle point, smallest element or smallest entry in its row. So I would go through each row and circle the smallest entry. So -4 in the first row, -1 in the second row, -5 in the third row. And then we're going to underline the smallest entry in, or the largest entry in every column. So first column, 12 is the largest entry. Column 2, -1 is the largest entry. And then column 3, 6 is the largest entry. And so we can see this -1 right here. We circled it because it was the smallest in its row, and we underlined it because it was the largest in its column. And so that is our saddle point. So our saddle point is -1. We also call that the value of the game. So both of those are -1, the saddle point and the value of the game. Now, there's a couple other things that you'll be asked on questions like this. You might be asked for the location of the saddle point. And the location of the saddle point is 2-2. So that is the second row and the second column. You also will sometimes be asked for the optimal strategies that produce that. So the optimal strategies. So the optimal strategies are for player A, and we put these in a matrix generally. You'll see why in the next video, why the matrices are the size and shape that they are. But that'll be explained in the next video. It'll make sense. For now, we just want to know how often is Team A going to choose option 1? Well, they're not going to choose option 1 because this is a strictly determined game. They're always going to choose option 2. So 0% of the time is how often they're going to choose option 1. Then we're going to put how often they're going to choose option 2. Well, that's 100% of the time. So 1, because the saddle point is what the team is going to choose every single time. And then how often are they going to choose option 3? That's 0. They're never going to choose option 3, so that's 0% of the time. So A's optimal strategies are 0, 1, 0. For Team B, their optimal strategy, so we write this one in a column matrix. And the reason why we're doing this, we're going to end up multiplying matrices in the next section. So that's why we have to put them in certain shapes. But again, that'll make sense later on. All right, so Team B, how often are they going to pick column 1 or option 1 for them? None of the time, 0% of the time. How often are they going to pick option 2? All the time, 100% of the time. every one of those options is negative, that's a great option for them. So 100% of the time. How often are they going to choose option 3? 0% of the time. They are never going to choose option 3. So in a strictly determined game, that is a game with a saddle point, the optimal strategies will always be 1s and 0s. When we talk about mixed strategy games, which is what we'll talk about next time, the numbers will add up to 100%, but they could vary. So maybe you've got 25%, 25%, 50%, or maybe you've got a third, a third, a third. So any three numbers that could add up to 100 would work as a mixed strategy. But like I said, we'll talk about mixed strategies next time. All right, so that's a saddle point. Again, smallest entry in its row and the largest entry in its column. All right, so let's move on to talk about dominated strategies. So we'll look at both dominated rows and dominated columns. So a dominated row is a row where each entry is smaller than each corresponding entry in another row. Okay. All right, so a dominated row, we're looking at row, so we're looking from player A's perspective. And this is important. We need to know whose perspective we're looking at numbers from. So player A's perspective, big numbers are good, small numbers are bad. Okay, so negative numbers are bad, positive numbers are good, but just in general, the bigger the number it is, the better for player A. All right. So let's look at an example. All right. So in this example, Team A has 3 options and Team B has 2 options. And then our matrix is 3, -2, 0, 8, 6, and 4. So it's a 3x2 matrix. All right. So what we want to do is we want to look for options that just wouldn't be good options. So, for example, rock, paper, scissors is a game that you're probably familiar with. And it's a game that we could draw out a matrix, a game matrix for. And in that game, each element, rock, paper, and scissors, each beat one other of the elements. And so because of that, there's this kind of balance. And really, any sort of game has to have some sort of balance where there are good options, but the good options also have some bad characteristics. So rock is good if you're playing against scissors. It's bad if you're playing against paper. So it has some good, some bad. And all games have these things because otherwise the game wouldn't be any fun. So a dominated strategy is just a bad strategy. If there was another strategy in rock, paper, scissors that beat all 3, rock, paper, and scissors, then you would never want to choose rock, paper, or scissors. You would choose the other thing that beats all 3 of them. So a dominated strategy is one that's just not a good strategy. It's one that you would just never want to play. So let's look. We're going to compare each of these 2 at a time. All right, so let's start off. Let's compare row 1 and row 2. Now we're gonna do this. We're gonna look at dominated rows, and then we're going to look at dominated columns in another matrix. But for the most part, you're going to be looking for both in the same matrix, and we'll do an example like that after we look at each one individually. But for our initial examples, we're just going to look at dominated rows here and just dominated columns in the next matrix. All right. So we're comparing rows 1 and 2. All right. So remember, for player A, positive numbers are good, negative numbers are bad. So we're looking for numbers that are bigger. So in row 1, the 3 is bigger than the 0 in row 2. And then the -2 is smaller than the 8. So row 1 does not dominate row 2. Row 2 does not dominate row 1. Because in the first comparison, so we're only going to compare up and down for dominated rows. So we don't compare the 3 to the 8. We don't compare the 0 to the -2. So 3 is bigger than 0, but -2 is smaller than 8. So neither of those dominate each other. All right, let's compare 2 and 3. So 6 is bigger than 0, but 4 is smaller than 8. So again, each row has one that's bigger, one that's smaller. So there's no domination there either. All right, our last comparison would be row 1 and 3. And so we have 6 is bigger than 3, 4 is bigger than -2. So both elements in row 3 are bigger than their corresponding elements in row 1. And so we would take row 1 out. This would be dominated. So what we would say is that row 3 dominates row 1. And if we think about it, it makes sense. If we think about it in terms of money numbers, if you have the option of either winning $6 or winning $4, so that would be option 3 for player A, or alternatively, you could choose to either win $3 or lose $2. Clearly, you would choose the option where you could either win $6 or win $4. Because both of those options, winning $6 and winning $4, are clearly better than winning $3 or losing $2. That would just be a terrible option. If this was a game you were playing with a friend where you stood to win or lose money, you would never choose option 1. It's a terrible option. So that's what a dominated strategy is. It's one that's just not a good option. So we would then rewrite our matrix with what we have left. So 0, 8, 6, 4. And we do go ahead and rename or renumber them. So options 1 and 2 and options 1 and 2, we take out option 1 for player A and we just kind of move it up. So that would be the resulting matrix after we remove the dominated row. All right, so now let's look at dominated columns. So a dominated column is a column where each entry is larger than each corresponding entry in another column. So let's compare those real quick. Dominated row, that was from player A's perspective, a row where each entry is smaller than. But dominated column, larger than. And that's because we're looking from a different player's perspective. So dominated column, this is player B's perspective. And remember, for player B, large numbers are bad. Small numbers are good, large numbers are bad. So we're looking from a completely different perspective here. All right, let's look at an example. So in our example, player A has 2 options. Player B has 4 options. So it's a 2x4 matrix. Our matrix is -8, -4, -6, -6, -3, 0, -9, 12. All right, so we need to compare. We're only looking at dominated columns here, but we need to compare each column with each other column. So this will take a little bit because we have a lot of different comparisons to make. All right, so let's first compare column 1 and column 2. All right, so the way I'm going to do this is a little bit different because we have to look at things from a reverse perspective. So rather than talking about negative numbers and positive numbers, I'm going to talk about winning and losing, which you may find easier, or maybe to you it's easier to think about the negative and positive. For me, it's easier to think about negative numbers being winning money and positive numbers meaning losing money, because that's the case for player B. So this -8 in the first row, first column, that is player B winning $8. That's player A losing $8, but player B winning $8. And dominated columns are from player B's perspective. All right, so when we compare columns 1 and 2, we have winning $8 and winning $4. So winning 8 is better than winning 4. And then we have winning $3, which is also better than winning $0. So column 2 is going to be a dominated column. It's dominated by column 1. And that's because -8 is smaller than -4, -3 is smaller than 0. Or winning $8 is better than winning $4, winning $3 is better than winning $0. All right, so now we've compared columns 1 and 2. Now let's compare columns 1 and 3. So winning $8 is better than winning $6, but winning $3 is not better than winning $9. So neither column 1 nor column 3 dominate one another. All right, let's look at column 1 versus column 4. So winning $8 is better than winning $6. Winning $3 is better than losing $12. So remember, positive 12, that's losing $12 for player B. So column 1 also dominates column 4. Again, because the values are smaller. -8, smaller than -6. -3, smaller than 12. All right, so column 1 dominates columns 2 and 4. All right. Now, we're still going to keep comparing things because even though columns 2 and 4 are dominated by column 1, they could also be dominated by other columns as well. All right, so now let's compare columns 2 and 3. So, winning $6, that's in column 3. Winning $6 is better than winning $4. Winning $9 is better than winning $0. So column 3 also dominates column 2. So right now we have columns 1 and 3 both dominate column 2. All right, so then we'll move on to column 2 and 4. So winning $6 is better than winning $4. Losing 12 is not better than winning $0. So 4 and 2, neither of those dominate one another. But we're done with comparisons for column 2. So what we know is that columns 1 and 3, 1 and 3 dominate 2, column 2. All right, so we've compared 2 with everything else. Now let's compare 3. We also compared 1 with each of the others as well. So now we need to compare. We've compared column 1 with columns 2, 3, and 4. We've compared column 2 with 1, 3, and 4. So now we need to do column 3 compared with column 4. All right. So we have. We'll put our little marks down there to indicate which columns we're comparing. All right, so we have winning $6 and winning $6. So those two are the exact same. So neither is better than one another. And if that happens, what we do is we just kind of ignore that part. Because if those don't matter, our first comparison in columns 3 and 4, then what does matter is the comparison of the other two elements in the column. And so we can see the -9 in column 3, that's winning $9. That's definitely better than losing $12. So column 3 is the dominating column. It dominates column 4. So even though the -6 isn't bigger than the -6, column 3 is still the better option because the other element, winning $9, is definitely better than losing $12. All right, so we also have columns 1 and 3 also dominate column 4. So it is possible for multiple columns or multiple rows to each dominate a single column or row. All right, so that's dominated rows and dominated columns. Let's look at one more example where we'll look at both. So in this case, we're going to try to find all dominated strategies, that is, dominated rows and dominated columns. And it doesn't matter which we start out with. We can start off with rows or we can start off with columns. Doesn't really matter. So I'm going to start off with rows. Let's compare the first two rows. 1 is bigger than -3. 4 is bigger than -2. -3 is not bigger than 0. Okay, so neither of those rows dominate one another. All right, how about 1 and 3? All right, 2 is bigger than 1, 6 is bigger than 4, -1 is bigger than -3. All right, so row 1 gets dominated by row 3 because each element in row 3 was bigger than its corresponding element in row 1. All right, last comparison here is row 3 and row 2. 2 is bigger than -3, 6 is bigger than -2, -1 is not bigger than 0. All right, so the only domination we have here is row 3 dominates row 1. So we would remove row 1 from our matrix. All right, so now let's look at dominated columns. So we only have to look at what's left over. We don't even have to include row 1 in this. So let's compare columns 1 and 2. So we'll do the winning and losing thing again. So winning $3, that's better than winning $2. losing $2 is also better than losing $6. So in this case, column 1 dominates column 2 because each value in column 1 is smaller than each value in column 2. This is the part that most people have the most trouble with because we're used to, in our minds, thinking about big values as good, smaller values as bad. But we have to shift our thinking when we're looking at dominated columns because everything is backwards when we're looking at dominated columns. So -3 is smaller than -2, 2 is smaller than 6, so the larger values, -2 and 6, those get dominated and removed. All right, so that was column 1 and column 2. All right, now let's compare column 2 and column 3. So column 2, -$2 is better than winning $0. Losing $6 is not better than winning $1. So 2 and 3, neither of those dominate one another. All right, and then finally, we'll compare columns 1 and 3. So we have -3, that's winning $3 is better than winning $0, but losing $2 is not better than winning $1. So no domination there either. So the only domination we had for columns was column 1 dominates column 2. And so our resulting matrix would be now a 2x2 matrix. -3, 0 to -1. And so that is our resulting matrix. Now, technically, what we would want to do here, since we started with looking at dominated rows and then switched to dominated columns, we would then want to go back to rows and make sure that the removal of that middle column didn't change whether there were going to be more dominated rows. So we could do that here. 2 is bigger than -3, -1 not bigger than 0. So neither row dominates either row here. So that means we are done. There's not going to be any examples where you have to go back and forth in the homework. So you can either start with dominated rows and then move to dominated columns, or do dominated columns and then dominated rows, and it'll work either way. All right. So again, to find a saddle point, we are looking for the smallest element in its row that is also the largest element in its column. And there won't always be a saddle point. Sometimes there won't be a saddle point, and that's actually what we're going to talk about next time. In the next section, we're going to look at we're going to look at mixed strategy games, and those are games that don't have a saddle point. So in this section, if there's no saddle point, that's the answer. We just say no saddle point. But in the next section, if there's not a saddle point, we'll figure out what that mixed strategy is. Dominated rows are rows where each entry is smaller than the corresponding entry in another row. So the larger rows dominate the smaller rows. And then for dominated columns, a dominated column is one where each entry is larger than each corresponding entry in another column. So smaller columns dominate larger columns because we're looking from player B's perspective. All right, that's it for today. I'll see you next time.